Lesson 6. Approximating a binomial distribution. Consider the binomial random variable. X follows the binomial distribution with n number of trials and a chance of success p. If we had to calculate probabilities for values of x where n is quite large, it can be quite difficult. In some circumstances, you can approximate a binomial distribution using a normal distribution. If n is large and p is close to 0.5, then the random variable x that can be binomially distributed can be approximated by a normal distribution with a mean mu and a standard deviation sigma, where the mean will be equal to the number of trials n multiplied by the probability of success, and the standard deviation will be the square root of the number of trials multiplied by the probability of success multiplied by the probability of failure, or 1 minus p. Here you can see the bars will represent the discrete values of x, and the smooth curve will show the continuous normal distribution. This approximation only works if p is close to 0.5, as the normal distribution is symmetrical. Let's do an example. A biased coin has the probability of tails is equal to 0.53. The coin is flipped 100 times and the number of tails, x, is recorded. Part A. Write a binomial model for x. Part B. Explain why a normal approximation, y follows the normal distribution with a mean mu and a standard deviation sigma, may be suitable for x. And Part C. Find the values mu and sigma in this approximation. For Part A, x will follow the binomial distribution with 100 number of trials and a probability of success 0.53. For Part B, the distribution can be approximated by a normal distribution since n is large and p is close to 0.5, which are the two conditions to apply a binomial approximation. For Part C, we know that the mean mu has to be equal to np, and so this will be 100 times 0.53, which will give us 53. For the standard deviation, we know it's the square root of np times 1 minus p, which will be the square root of 100 times 0.53 times 1 minus 0.53, which will give us around 4.99 to 3SF. You may have noticed that the binomial distribution is discrete, but the normal distribution is continuous. To make up for this, we need to apply a continuity correction when calculating probabilities. For example, if we have x that is binomially distributed with 14 trials and a probability of success 0.5, approximated by y following the normal distribution with a mean of 7 and a standard deviation of 1.87, then if we try and find the probability that x is greater than 5, that means everything 6 and onwards. But because 6 and 5 have the middle ground, 5.5, and we want everything above 5.5, it can be approximated as the probability that y is bigger than 5.5, as y is continuous. For probability that x is equal to 7, 7 is halfway between 8 and 7, and 6 and 7. So this will be the probability that 6.5 between 7 and 6 is less than y, which is less than 7.5. And for the probability that x is less than or equal to 4, it ends between 4 and 5. So this will be the probability that y is less than 4.5. And a full table of the continuity correction can be seen on screen. Let's do one more example. X follows the binomial distribution with n equals 150 and p equals 0.48, and this is approximated by the normal random variable y, which follows the normal distribution with a mean of 72 and a standard deviation of 6.12. Use this approximation to find the probability that x is less than or equal to 70, and the probability that 80 is less than or equal to x, which is less than 90. Part A. As we want the probability that x is less than or equal to 70, this will be approximately the probability that y is less than 70.5 as we add the extra half. And so using the normal CD function, this will give you about 0.4032 to 40p. For Part B, using the continuity correction again, this will be approximately the probability that 79.5 is less than y, which is less than 89.5, which again using the normal CD will give you about 0.1081 to 4dp.